We're going to continue our talk, kind of the last piece to the puzzle before we get into motors, generators, um, and combining magnetism and electricity. We're going to get into it's going to lead you into a lot of the application and a lot of the things that go on in this world as far as how you generate electricity, motors, and we're going to bring back into force. It's also going to help explain the statement we made earlier when we did light and called it self-propagating, of how it drives itself and how light can actually travel through a vacuum. It's not a mechanical wave. It doesn't need a medium to travel through. And how the EM spectrum, electromagnetic spectrum, comes into play, of how the electric side of this wave helps propel itself because it also has a magnetic side of it. And so we'll explain all those things and why they're perpendicular. So, to kind of break it all down into its base layer, we're going to look at charged particles in a magnetic field. Okay. Now, if you have one thing you want to talk about is you have this magnetic field, an external magnetic field. If you have a static charge, an electric charge, an electron, proton, doesn't matter, positively charged object, negatively charged object, and it's just sitting there, it's not moving. There's not going to be any force felt by that charge. The magic happens is when one of those things is moving. Something has to be what they always talk about, being dynamic. Either your magnetic field is going to be changing, or more commonly, your charge is moving, dynamic, moving. When that comes into play, you now are going to have a force being applied. And if you have a force being applied, you can actually start to cause an object to change its motion. So you can steer that charge, or you can get a magnet to start to move, aka get a motor to move, or vice versa. You get a magnetic field moving and changing on a charge. You get that charge to moving. You get electricity, a generator. So as we look through this, you're going to look for a couple of things. The first thing you're going to have is some kind of charged object, charged particle. You're going to have an external magnetic field. And the kicker is, and this is usually the big one, if one of those is moving. So in this chapter, we're going to talk about if the charge is moving in that field, you're going to feel a force. That charge is going to feel a force being applied. Okay. And so you're going to have those three things. You get this magic thing having a force being applied, and that can either, depending on the situation and how the setup is, you can either have charge start moving faster and in a more direct way, the flow of electricity, current, a generator, or you can get an object to start to move, a magnet, the attached to, say, a metal rod, a shaft of a motor start to spin. And so this is kind of the magic. Now you go back to our electromagnetic spectrum and self-propagating waves. If you have an electric side and a magnet side, and one of them's changing and moving, it's going to apply a force on the other. Well, that one's now going to start moving and changing, which is now going to cause motion on the electric side, and vice versa. So it self-propagates, and we'll talk about that a little more. We're going to have another right hand rule. It's not going to be the right hand curl rule, but we'll get to that here in a second. So the basics of 19.3, here's chapter 19, section 3, is that a charge moving through a magnetic field is going to experience a force. Okay. And again, that force is now going to allow you to cause a change in motion, going all the way back to Newton's laws. All right. Now, the relationship is you're going to feel max force when those things are perpendicular. So you're going to have a magnetic field in one direction. Say your magnetic field is in this direction. Okay. To feel the max force, the speed, that charge of that charged object, say this little particle, would have to be traveling at a certain velocity, say in this direction, perpendicular. It's going to feel the max force. Now, how much that is, that's what we're going to look at with the calculations, with the equation. The direction, we're going to use a right hand rule. not right hand curl rule. That was last chapter, right hand rule. Okay. And so again, we're not going to get into the angle game, but understand this is under using this equation, you have to have them be perpendicular to each other. If not, you'd have to either find the component of the magnetic field that's perpendicular using your right triangles, or you could use the velocity, depending if it's moving at an angle, the velocity vector that's perpendicular to the magnetic field. So you might have to use sine cosine. We're not going to get into that. We're just going to kind of simplify it. But you can see here the force being applied by this magnetic field is going to be based on the charge that's moving in it times its speed. Okay. So these two are talking about the charge that's actually moving and how fast, coulombs, meters per second, and then you have your strength of your magnetic field. A lot of times you see it rearranged this way, either or, it just depends. Usually I usually use the other one just because it's cleaner and it's easier for me to remember. But this is kind of the standard form. Again, external magnetic field, the force being applied that charge feels, the amount of charge, how fast that charge is moving. For some of you guys that have heard of rail guns or in some of the kind of the space age, and the Navy does have some of these. They're talking about launching rockets this way using magnetic fields. Maglev trains use this to propel, and so they'll create a charge that's moving. They'll have a certain magnetic field, and you can get a certain velocity vector or a force being applied to that object, that projectile. All right, so just talking about, again, has to be perpendicular for max force being field. Your magnetic field strength has to be in Teslas, like we've talked about. Charge has to be in coulombs, so make sure you're using good scientific notation and careful with your parentheses. And your velocity has to be in meters per second. And force, as always, is in newtons. Okay. Your right hand rule. Okay, so you're going to use a right hand rule. Now, understand, and this is where, remember I said earlier, Ben Franklin's going to tick you off. This is for a positive charge, your right hand rule. If it's a negatively charged object, and I'll give you a couple problems with it, you can either A, say, okay, I have to use my left hand rule, or most of us will just use the right hand rule, and just whatever result you get from it, understand it has to be in the opposite direction. Okay. Your thumb always points in the direction of this velocity vector. So what direction is that charge moving? Your fingers then are going to point in the direction of the magnetic field, and then the force vector is actually going to be the direction your palm is facing. Okay. So for instance, the example I drew earlier, I said the magnetic field was in this direction, the velocity vector was up. Okay, so my thumb in this direction, I know you can't see my hand, but my thumb would be going up my computer screen. My palm would be facing to the, or my fingers, I'm sorry, would be facing to the right. My palm would be facing into the computer. So I have to use that dot or cross like we did with magnetic field. The force vector would be into the page because that's the direction my palm would be facing. Okay, think of the arrow. Tips coming at you, you see a point. The X, you see the feathers moving away. So thumb in the direction of the speed or the velocity vector where the charge is moving, the positive charge. Your fingers are pointed in the direction of the magnetic field, and your palm is now facing in the direction that force is going to be applied. Right hand rule, again, for a positive charge. So let's just apply a couple problems real quick here. A big thing here is being able to apply this right hand rule. So proton, so I'm dealing with a positive charge. Magnetic field is 4.2 times 10 to the negative second. I'm going to try to find the speed and the magnetic force that it feels is 2.4 times 10 to the minus 14th. All right, so I'm just going to use my force equals QVB. Okay, my force is 2.4 times 10 to the minus 14th. The charge, it says, is a proton, so it's 1.6 times 10 to the negative 19th coulombs. Velocity times your magnetic field of 4.2 times 10 to the minus second. Again, being very careful with your parentheses, you should find out that the speed is 3.6 times 10 to the sixth meters per second. Your speeds will be high if you think about the speed of light, 8 times 10 to the 3 times 10 to the eighth meters per second. So it will be relatively high when we're talking about this. Now, you can't tell direction because all it does, for one, it's asking magnitude. But the direction, you don't know the direction of either or. You don't know the direction of the magnetic field. You don't know the direction of the force. So you couldn't use the right hand rule. It's a good thing because they only ask you for the magnitude. All right, now I got an electron, so I'm going to have to be careful. Beam experiences a downward force, okay, while traveling. So downward force means it's going to be into the page. Okay. Now, why do I say that? Because they give me a west direction. So if it meant actually down the page, they would have said south. Because they give you this west, when they say downward, that's telling you it's into the page. Okay, they're telling you that that's 2 times 10 to the negative 14th newtons. A magnetic field west of 8.3 times 10 to the minus 2 Tesla. What is the direction and magnitude of the velocity? All right. So again, force equals QVB. My force is 2 times 10 to the minus 14th. And I'm not really going to worry about positives and negatives in here. We'll worry about direction with the right hand rule. 1.6 times 10 to the minus 19th because it's an electron. V times the B would be 8.3 times 10 to the minus second. Plug and chug. And you should get a velocity of 1.6 times 10 to the sixth meters per second. Now it's my magnitude. The direction. Now, if you apply the right hand rule, okay, fingers go in the direction of the magnetic field. So my fingers right now would be pointing to the left, to west. Okay. My palm is going to be facing into the page. Okay. So if I now extend my thumb would be pointed south. Now, it's not my answer. This would be the direction of my thumb. Again, I pointed my fingers in this direction here. This would be my thumb. Oops. My palm now is facing into the page, so I can't see my palm because that's my force vector. And if I extend my thumb, it would point down, south. Now, because it's an electron, remember, your right-hand rule is good for a proton. So either A, you have to realize, okay, since my thumb is south for a proton, opposite would be to the north for an electron. So north is my direction because it is an electron. Or you could apply your the left hand rule. Now I usually don't do that because I don't want to remember a second rule. So if you use the left hand rule, same thing would apply. My fingers would point to the left, to the west. My palm would be facing in to the page away from me into my screen. My thumb extends up, it would be going north. So however works best for you, just understand I had to go opposite because I'm dealing with an electron. The right hand rule is good for a proton because remember, early on, everything was based around protons. So my answer twofold, direction and magnitude. Okay, number 3 here. Uniform 1.5 Tesla is pointed north. And let's try that a little better here. So 1.5 Tesla, that's my magnetic field. Again, it's an electron. It now has a speed of 2.5 times 10 to the seventh through this field. It is the electron is moving vertically downward. Okay, so that tells me downward into the page would be my velocity vector. Again, because they told me north, south would be down my page. Downward in this case is into the ground. So the velocity vector would be 2.5 times 10 to the seventh. So you go back to QVB, 1.6 times 10 to the minus 19th. The velocity of 2.5 times 10 to the seventh. Running out of room here. And 1.5 Tesla. So when you plug and chug, you'll find a force of 6.6 or 6 times 10 to the negative 12th newtons. Now, what is the direction? Now, it's an electron. Now, if you apply the right hand rule, your thumb would be into the page. Your fingers would be pointing up. My palm, okay, would be facing east if you use the right hand rule. Fingers would be pointing up north, up this page in this direction. This would be my fingers. My thumb would be into the page. My palm would be facing to the right. Now, because it's an electron, it's going to be opposite, so the direction would be west. So this would be my fingers. This would be my thumb. Okay, and if you do that, your palm would be facing east, but that's for a proton. You need to understand and remember that it's going to be opposite, so it would be west. Or apply the left-hand rule as well. All right. Now, some interesting things occur here. You can get charges to start to curve. So in this case, you have a magnetic field into the page. You have a charge, okay, that is moving to the left. So if you apply your right hand rule here, I'm sorry, it's not applying, it's moving in this direction. So fingers would be pointed into the page. My thumb would be moving in this vector here. So here, let me change, get some. So this would be my thumb. Okay. My fingers would be into the page. My palm would be facing in this direction then. And this charge, then you would start to get a circular motion and get a certain nice circular motion. Okay. If you go back to our centripetal motion, there is your centripetal force causing it to continually curve, 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 curve. You cut that off, it's going to launch. Now, let's apply this to electricity. What is current? It's the flow of charge. So remember, that's you have a certain velocity. It's moving a certain velocity, certain meters per second. This amount of charge is moving at a certain rate. So now, if I get electricity current moving through a magnetic field, I can actually start to cause it to apply a force to it. So again, let me back up and go back to this. What to slide up? There we go. So if you have a wire, charge is moving up this wire. If it's in a magnetic field, so you turn the electricity on, okay, through this bar, your thumb would be going up the page. Your fingers would be going into the page. This rod is going to now feel a force to the left, and this is your rail gun. This would be a train that's on a maglev rail system. You can start to get this to launch, and based on the strength of the magnetic field or the rate the current is flowing, you can change that amount of force that's being applied to that bar and launch it at a greater and greater force. Once you have the force, if you know the mass of that projectile, the train, whatever you're launching, you can figure out the acceleration and then get into your kinematics. So if you equate that to our different charges or our last formula, depending on force, we had to worry about speed. So now I'm going to apply and kind of convert that into current. I have a certain magnetic field, and now I have to account for how big or how long this wire or that object is, because that's going to give me more charges moving. I'm going to have a greater force. Okay. So looks very similar, and we could do some factor label and some substitution. I'll save you the pain. That force, should look very similar. Your current and your length is going to take into account the amount of charge and the velocity. So you still have the magnetic field strength. I now have this current in amps, and I have the length of that object, in this case, the wire that's in that object, or that's in that magnetic field. Your right hand rule is still going to apply. So if you have two wires next to each other, okay, if you use your right hand curl rule, okay, so this I1, thumb goes up, your fingers curl around there. So I have a certain magnetic field being applied. Okay. Over here, I have a certain magnetic field being created by this. So if you have two wires that are flowing next to each other really close and a very high current, you can actually get those wires either A, to move towards each other, bend towards each other, or move away. In computers and in circuitry, or if you're doing speaker wire or high end video cable, you have what we call shielding, Faraday cage, which does help eliminate this, because if not, you're going to be applying a force to the signal that's going through the audio or the speaker cable or computer, and you're going to have distortion. So if you have to run any type of wiring close to each other like that, you actually have to run them perpendicular to each other so they cancel each other out. So, but that's why your higher end audio visual cable will have basically a metal sheeting inside of there to cause the shielding, the Faraday cage, so that this effect doesn't happen. Flip them. Okay, your right hand curl rule, you get the magnetic field being the opposite direction, you're actually going to get these wires to move apart or bow away from each other. Oh, coming back to acoustics. Okay. So I have a magnet here, permanent magnet on your speaker. You have a coil of wire that your speaker signal comes through. It's electricity from your receiver or your iPod or whatever you're listening to, your iPhone, and you vary that current. You're varying the force, which is going to cause a force, which is going to propel this speaker forward and backward. So when we did the acoustics section and sound, and we talked about the speaker moving in and out, compressing, uncompressing the air, you back that up and you look at the magnet and the coil of wire, you're creating an electromagnet. Okay. Now, remember, when you have current going through here, current is moving charge in a magnetic field because you have a permanent magnet. And based on how much charge you have moving through here, the current, it's going to apply a certain force to it and either cause it to compress, move out, or decompress the air. And so that's how all your speakers, your earbuds, everything else are working. So you have a 6 meter wire carrying a current of 7 amps towards the positive X direction, magnetic force of 7 times 10 to the negative 6 newtons, X on a wire in the negative Y direction. Okay? So let's just draw a very simple diagram here. So you have a length of 6 meters, units are good there. I have a current, which is the flow rate, coulombs per second, of 7 amps, and it's feeling a force of 7 times 10 to the minus 6th newtons. You have a force in the y direction. You have a current in the positive I or in the positive x direction. Okay. Force is BIL, Bill. And you'll get 7 times 10 to the minus sixth, your magnetic field strength. Oops, I'm sorry. That would be your, hold on here. Skipped a step for you. The current is 7 amps and the length of the wire is 6 meters. So now you can solve for magnetic field strength, 1.67 times 10 to the minus 7th Tesla. That's your magnetic field. Now, what is the direction? Use your right hand rule. This is this is your velocity, in other words, because that's the flow of charge. So put your thumb in that direction. Okay. Your palm is going to be down the page. You have to kind of orient this a little weird. So your thumb is here. Okay. Your palm, because that's your force, is in this direction. This is your thumb. And if you're using your right hand rule, your finger should be coming out of the page. Okay, so that magnetic field is out of the page. And let's look at one more practice problem here. We have a wire of length 1 meter, magnetic force of 0.5 newtons. Due to perpendicular uniform, if the wire carries a current of 10 amps, what is the magnitude of the magnetic field? Now, all it's asking is magnitude. Okay. So, Bill, F equals BIL. You have 0.5. The current of 10 amps and the length of 1 meter. And the magnetic field strength would be 0.05 Tesla. Okay. Now you can't find direction because they don't tell you any of the directions. They just tell you they're perpendicular. As always, if you have questions, concerns, make sure you sign up for the Zoom meeting or email me and we can get together and go through this stuff.